we've dealt with a couple of these vectors before. First, typically represented by delta x in formulas is displacement. That is the vector distance between two locations. So just from start to finish, what is the straight line between these two physical points? We're most often going to measure that in meters. There will be questions that use other units, but meters is the nice normal one. Good question. When I'm talking about vectors, I tend to write this symbol above them to show it's a vector. There's a couple different ways you can do it, and keep forgetting about this fact. These notes, and the computer writes it in such a way that the line is under it. For all of these, the line under the V, the X, and the A just means vector. Notice time isn't a vector because you can't have 3 hours north. It doesn't have that line. Same with 1/2 and 2. Additionally, I'm going to deal with this later, but since these velocities are squared, they kind of lose their vector direction because when you multiply two vectors in a specific way, they stop being vectors. So these two lose their vector signs. Same here, you multiply two vectors together, it just goes away. Great question. That does not mean that equal is a vector. It does not mean that equals itself is somehow a vector. 3 lines there is like equals sign plus. It means equals if you're working it in math, but it's the official definition of means that the definition of velocity is change in displacement over change in time. This means is defined as. Velocity is defined as change in displacement over change in time. So it's, in terms of the textbook, it is more powerful than an equal sign. Equals means these two things happen to be the same number. This means these are always the same because they are defined as the same.
So that's the best
It is not imperative. Only 2 of the formulas up here have it because only 2 of them are formal definitions. These 2 don't because they're just normal non-definition formulas. And anytime you see this, it's mathematically the same as an equal sign. You're going to treat it like one when you're doing your math. The textbook likes to use it to make things more important. So that is what it means, and there's nothing to worry about whenever it comes up or it doesn't come up. But it is handy because if I ever ask you, what is velocity? Velocity is defined as change in displacement over change in time. Several physics concepts are the formula because physics at its most basic is using math to explain everything to the best of our ability. And so that means we take everything and turn it into the math version of it. So if you look up the textbook definition of velocity, velocity is speed with a direction, it is displacement over time. This definition right here, velocity is displacement over time, is that. So this is the math form of those words. All of physics is going to be a constant back and forth between definition and the math equivalent of that statement. We are translating numbers into words and vice versa. So, line under the letter means variable, triple equal sign means definition, just a fancy equal sign. The delta x's all refer to change in displacement from start to finish, just the distance between 2 points. We do care about the direction. Velocity is defined as the change in displacement over time, In order to have a velocity, you need to move somewhere, and it will take some amount of time. So 20 miles per hour, you move 20 miles in 1 hour. 3 meters per second, I walk 3 meters in 1 second. The most common velocity unit we're going to use is meters per second, but the homework question we're going to look at uses miles per hour as long as it's some unit of distance over some unit of time. It counts as a velocity. Well, it counts as a velocity if you have a direction. If you don't have a direction, then it's just speed, which is the scalar form that lacks specific direction. Like when you're driving, your speedometer doesn't care if you're going up, south, north, down. It just tells you the number. You have to look at a compass to figure out the direction. So, displacement, change in displacement over time. The last remaining vector letter that is currently in these formulas, I'll go ahead and define it, is acceleration. Acceleration can actually look right here for its definition, because acceleration is defined as change in velocity over change in time. In order to accelerate, you need to speed up or slow down, and that will take some amount of time. So you hit the gas in your car, you go from 0 to 60 in 3 seconds. 0 to 60 is a delta V, so 60 divided by 3 seconds, that's pretty fast. So, acceleration, change in velocity over time. Sorry, I didn't catch that. The most common unit for acceleration is meters per second squared, because to get acceleration, you divide velocity by time. Meters per second divided by seconds creates this. And I'm going to use the word accelerate to refer to speeding up or slowing down, because in terms of physics, there's no difference. Changing speed at all is an acceleration, technically. If you're moving forwards and you get faster, you're accelerating forwards. If you're moving forwards and slowing down, you're accelerating backwards. It is a vector, so the direction still matters. And these are the 3 starter vectors, and they are all intrinsically connected, because we've got basically the first. This is the first one divided by time. This is the second one divided by time. And that's what the first 2 formulas are. The next 2 is additional ways that they all interact, which we'll be spending more time with in the coming weeks. For right now, we're just going to focus on the first one as we look at the homework assignment. I'm cutting 20 because as I was rewriting the assignment, I said to myself, I don't like how that's worded. I'm going to change it. And then I did. So 20 is not very user-friendly the way it's currently worded. You can just ignore it for right now. The others, though, we will pay a little more attention to. Starting from 16, well, let's look at 16 and 17 at the same time, because they're basically the same thing. For both of these questions, we are given a velocity vector. In 40, we are told a car is driving 40 miles per hour east, and in 17, we are told a car is driving 60 miles per hour at this angle north of west. That would look something like this. And in each of these questions, we are asked, what is the displacement of this car if you drive that speed in that direction for 0.3 hours, excuse me. And for any physics question, standard operating procedure, this will get you through really any math class that uses algebra. Read the question, list what it tells you. So for 16, we're told 40 miles per hour east, time of 0.3 hours, and we are asked to find delta x, the displacement. Once you've listed this, you look at your formula sheet and you ask yourself, what formula present has all of these in it? The things I know and the things that I want. And starting out simple, this is the formula that contains all those things we care about at the moment. V equals delta x over delta t. So we rewrite our formula, start plugging things into it, and then we be very careful about algebra, because a couple of people have looked at this and said, so we divide 40 by 0.3, right? So write it, stare at it, then so we're just going to multiply 0.3 on both sides, and that is how far we would drive. Yes?
So we assume that 130 is the change in time?
Yes. A car drove 40 miles per hour east for a time of 0.3 hours. So from the beginning of the experiment, this is how fast we moved in this direction, and we were doing it for this amount of time. And 17 works just the same way. Plug in 60 instead of 40, same amount of time. That will give us a different distance, or a different displacement. And for both of these, since we're asked for displacement vector, just displacement will inherit the velocity vector that created it. So if you're driving east, you're going to displace east. So for 16, 12 miles east, 17, 18 miles in that direction.
Would it be possible to do 17 without drawing an angle?
Say that one more time.
Would it be possible to do 17 without drawing an angle?
Yes. Like to get to this answer, the picture is not really required. When I was working this before, I just drew it to show how to draw out this, because some of my students are still getting used to that type of notation. So I included this picture just to show that you start west and then you tilt this far north. In terms of what you actually need for this question, you have variables, formula, work, and the answer itself. And because we were asked for displacement vector, a vector needs magnitude and direction. The answers 17 and 16 need directions. So, another glitch when I was rewriting this assignment, 18 is used twice. This is supposed to be 19. It is referred to as 19. So this is the original 18. Number 18, you're asked to graph these two displacements and show what they would look like added together. So we have one vector pointing due east, one vector pointing in this direction, relative to tail. If someone was to actually drive this, then this would be the displacement start to finish. That triangle is the same shape as the triangle if you were to add the velocities together instead of the displacements. Yes?
So when you start, or when you start that at zero,
Come again?
like, would you not, when you for that, like, when you start on zero, that will scale on zero?
When you are drawing vectors in order to add them together, it helps to draw them one right after the other. Because if I was to say, start at the origin and draw these, drawing a line between these two things does not represent the sum of the vectors. Because if you were to go east and then go northwest, you would end up north and still a little bit east of where you started. But if I was to try to connect these two lines, that doesn't really tell me much. And that's because this has drawn the two of them completely separately. In order to actually add them together visually, you need to put them one after the other, one's tip on the other's tail.
So what would have drawn
Well, since we're adding them, that wouldn't actually matter much. Because if we drew 17 first, we go in this direction, then we would go due east, and the sum would point in the same direction as the red line over here. So as long as they're being added, it doesn't really matter what order you draw them, as long as it's tip to tail. It might be a little easier to see if we get it on the same picture. Either way, you could just form a big trapezoid if you wanted to. Yes, for this particular assignment, when asked for the graphical method, drawing the triangle is the answer. This is to help set up future triangles that we will be drawing. Now, the problem that should be number 19 will kind of step on from there. In 19, we are asked to add velocities together. And even vectors that are invisible in normal life, like you can't really see force, you can't really see acceleration, even those vectors, you can still draw a triangle and do trig to add them together or break them into components. They're just not easily visible to the naked eye. But all vectors, no matter what kind they are, you can make into a triangle and add it together as long as they're the same type of vector. This is pretty, I'd say that this is easier to see with a vector like force. Let's say someone is pushing north on this box at the same time as someone pushes east on this box. What direction is the box going to start moving in? Yeah, northeast. So these two vectors, even though they are not physical displacement, you can still add them together and they will create a bigger net force in the northeast direction. So all vectors of the same type can be added together, but you have to add them together trigonometrically. You have to add x's to x and y to y. So for number 18, when you're asked to add the velocities from 16 and 17, we need to take those velocities and divide them up into their xy components. Because just adding 40 to 60 won't help us, because they're in different axes. And the reason why the other 18 came first is because even though this is a displacement triangle, it's still the same shape that the velocity triangle will take. Because the velocity vectors are in the same direction as these displacement vectors. So even though we made this for physical direction, physical displacement, it's still going to be the same shape, and we can kind of base our trig on this drawing, which is what this is. The green line is our first vector, 40 miles per hour to the east. Thankfully, that one's already divided into its xy components because it has no y component. So if I was to list those in coordinate form, it would just be 40, 0. 17 will take a little bit of trig, but thankfully, for the 60 miles per hour at the 68-degree angle, we know that angle and we know what axis that angle is from, so we can draw in our triangle legs to help us determine what direction everything points in and figure out what those components are. And just a little bit of trig to show where the answers came from. Sine of 68 would be the y leg over 60, cosine of 68 would be the x leg over 60. Okay. Now I saw what you wrote, and I see you correcting it. Very good. The thing about this second vector is that it's pointing north and west. So that west is going to work against our starting east, which is why I added that negative sign. So as a result, we're going to end up, like our final display, or our final velocity will be smaller in the x-axis than I use by itself. So written in this form, 17.5x and 55.6y is a perfectly satisfactory way of stating the answer. What this would mean is, for the final velocity vector, like the actual velocity you would get by adding these things together, if this was your velocity, you would go in, like if you were moving at this velocity for 1 hour, you would move this far in the x-axis and this far in the y-axis in 1 hour. So velocity in 2 dimensions is just you are moving so far in both axes at the same time. And that's all you need for, this is technically number 19, because this tells us the vector sum of those two velocities. Now, adding them together like this doesn't really make much sense for, say, one car that does one and then does the other than, say, looking at the total net velocity of the entire trip. But hypothetically, a different situation where this might make a little more visual sense is if the car was driving like this and there was a massive wind blowing it in this direction at the same time. So you try to drive east while a tornado blows you northwest, you're going to end up there. So all vectors of the same type can be added together. You can add displacement, displacement, velocity, velocity. That segues into the last question of the assignment. Could you add two vectors of different types together? For kind of an extreme example, could you add displacements to force? It'd be the same as trying to add shoe size to temperature. Similar, at least. I know that no matter how similar the two vectors in question might be, as long as they are different vectors, they cannot add directly together. There will be times in 1500 where we'll be making several triangles that look very similar to each other, like sort of on top of one another. A very common type of question that will come up is the case of a river. You want to float across the river, but the river's flowing this way, so you end up going that way. And that physical triangle could be used to represent the displacements or the velocities. Like say how wide the river is, how far downstream you end up, how fast you're going across the river, how fast the stream is flowing. And they'll be the same shape, they'll have the same angles, but the vectors it gives you for displacement, you can't put on the same triangle as the velocity ones. Not exactly the same triangle. If they have different units, they cannot be added directly. And that should be all the information you need that is needed for this particular assignment. And that is our introduction to vectors. Do you have any questions about anything from this page? And if not, from anything else from the assignment as a whole?
15.
15. Don't remember which one that is. It's displacement of Jimmy. Okay, great question. Are you comfortable if I erase all this? Cool. I'm going to scroll down, use the big graph for the drawing. So 15 is going to be like just chain adding a bunch of displacements together all at the same time. And I'd say for a lot of vector questions and questions about physical systems, drawing a picture first is usually a pretty safe first move. Blocks, blocks, blocks. So, let's draw a picture. These are all longish. So, Jimmy is going to walk 3 blocks east, starting from origin 1, 2, 3. then 5 blocks north. 1, 2, 3, 4, 1, 2, 3, 4, 5. And then the equivalent of 8 blocks at an angle 35 degrees south of west. Oof. Okay. So from this point, if we treat this like a new origin, we walk this, and now at that spot we're going to turn into this new direction. The direction is 35 degrees south of west, so we start west, and we're going to tilt 35 degrees south from there. And that is 8, a hypotenuse of 8. This might no longer be a scale. 1, 2, 3, 4, 5. That's just a little longer. That's probably close to scale. And the final question is, what is the displacement from start to finish? So we are looking for the thing that we ultimately want is distance here. Now obviously that does not form, all of that taken together at once does not form a triangle. So instead we're going to make triangles out of it. This is our origin. So in order to describe where we end up, we need to know how far south and how far west we are from the origin. So the answer we're going to be looking for is these little triangle pieces. You just want to know from start to finish, where are we in relation to the PI?
So like this, drew the triangle right there. In the top part of the triangle. So we know all the way out.
Yes.
I'm trying to, CX is going straight up.
Oh, to here?
CX.
Oh. Yeah. So the final answer is the distance between the origin and where we end up. So I kind of wound up chewing over it several times. That was where we started. And this is where we wound up. So this is the ultimate vector, and then these legs would represent the sides of it as a triangle. Now, how you draw that ultimately isn't a huge factor. I'd say drawing in the 8 triangle is a little more important, because in order to get the final answer, we're going to need to add 3 vectors together, 3, the 5, and the 8. But they're all in different axes, and 8 specifically has both an x and a y component. So in order to add them together, we're going to need to find what that x and what that y are. So a little bit of trig. Hypotenuse is 8. We know 1 35-degree angle. Yes.
Should those CX be ones different?
Can I call them something different?
Yeah, shouldn't C1 be CX? C1.
Yes, it should. It should. And I'm a human who makes mistakes. Thank you for catching that. I apologize. twice the scale at all. My apologies. This should have been a much shallower angle than I actually made it. I have to resketch this in a sec. Yep, I need to resketch this. I want to resketch this to make it a little better with drawing.
Well, is that the same idea? It's just behind scale?
Yeah, the scale is off. That line should be pointing in this direction. This should have been a shallower angle, so it's pointing this way instead. And as a result, the final vector actually looks something like that. I don't want my shoddy drawing to affect your perception of the answer and how you're doing. Because if you work it right, it's not going to look like the picture right there. So from here, the x component would actually be going to a little more like that. So the final green line would actually be in the second quadrant instead of the third.
With a triangle green,
The x piece would go to the left and the y piece would go slightly up. Well, okay, since we were given it in terms of cardinal directions, you should have some amount west and a small amount north. That's your answer. All right, can you tell me those numbers just to check so I can check them? Very good. Okay, so to get our final answer, I'm just going to literally add up the components. Our first vector was 3 east. I represent that as 3, 0. Our second vector was 5 north, so 0, 5. And then the third vector, both of these are pointing in the opposite directions. We have west and south, so that's going to be negative 5.5. Sorry, negative 6.55, comma, negative 4.59. And to get the final answer, we add up only the x's. That should give us negative 3.55, which would point west, and the y's would be negative 0.41. Oh, it would, thank you, sorry. And our units would be blocks. That is an acceptable way of writing the final answer. And 3.5. I'm on up to drawing wound up pretty to scale. Much. I'll see if I can have this graded for you by Friday, and we will, on that day, begin looking at new laws and more vectors. Any questions? How do you feel about this?
The most difficult part is probably being trying to try this. The way I drew it, confused me about
I know from my own experience, like what I've gone through with these is, if the picture, it is hard to draw them to scale going in from vertical, unless you have a ruler and you've set up a scale beforehand. And if the drawing isn't to scale, that might end up, for myself, that has wound up affecting my perception of what the answer should be, until I look at my work and fix the drawing based on that. Drawing the triangles can be tricky, because even if you get the lines in, where do I put the legs? And that's why, it's one reason why we're talking about it now, so that it's less scary than 1500. Any other questions? Do you have a wonderful day?
See you Friday.
Yes, we will have class Friday.